Welcome you to today's Distinguished Speakers Seminar in the Electrical and Computer Engineering Department. And it's a pleasure today to have Professor Ted Rappaport as our speaker. Professor Rappaport is well known to anybody in the area of wireless communications. He is presently the David Lee Ernst Weber Professor of Electrical and Computer Engineering at New York University's Tandon School of Engineering. And there he's also the founding director of NYU Wireless. Prior to that, he was at UT Austin, and prior to that, Virginia Tech. At each place, he has established very vibrant research centers related to wireless communications. He's also the author of several textbooks widely used, and is certainly one of the most influential people in terms of wireless communications, as well as the adoption of standards and now pioneering millimeter wave communications. So it's a real pleasure to have him with us today, and so let me turn it over to Dr. Rappaport.
Thank you very much. Thank you, Professor Stansel, for that very kind introduction. Good morning, ladies and gentlemen. It's a pleasure to be here at NC State to talk with you about a topic that you've probably heard a lot about already in the popular press. How many of you have heard about 5G? It's kind of hard not to hear about 5G these days. In fact, the IEEE has made 5G one of its core focus areas for the next year and a half in terms of continuing education and IEEE journals, transactions, special issues. Everything's talking about 5G. And so in that sense, it's wonderful. 5G is wonderful because it's going to be millimeter waves. It's wild. It's wild because it's wide open. No one knows what 5G is yet. In fact, industry practitioners all over the world are right now defining standards for what your 5G cell phone will do. It's wide open. Just like Uber and YouTube and so many applications that we now use regularly have been enabled by 4G, by the LTE bandwidth on today's cellular telephone, there are going to be new applications you can't even imagine coming in the next 3 to 5 to 7 years that will change our lives the way Google and Facebook has changed our society. Because 5G is certainly wide open. And this is all going to be enabled by the move to millimeter wave wireless communications. Because just like the oil industry has seen a glut of natural gas and oil that 5 years ago could not have been predicted through the means of fracking, we're going to see spectrum completely change the way wireless carriers and service providers and consumers use wireless in ways we've never seen before. And so that's what this talk is about, the wild, wonderful, wide open, but very challenging world of what wireless will be in 5 years from now, and certainly in 10 years. The first thing that is real to all the cell phone carriers and to the companies that ride, sometimes for free and sometimes pay over the top on wireless and wired means. Fact is, consumers are consuming data at a much greater rate than current capacity can keep up with. Every man, woman, and child in the world is consuming data at 50% per year consumption. In fact, in developed countries like South Korea and the U.S., where fiber is pretty prevalent in the urban areas, this is more like 100% per year. Double consumption each year if you looked at the amount of bits per second that you download on your smartphone. Doubling every year. And this is predicted for the foreseeable future. Not just the next few years, but for the next 15 to 20 years. In fact, Intel has predicted it's going to be much greater than that, with new applications that we can't predict today that will be enabled by massive broadband wireless to your mobile device. And if you look at the 4 generations of cell phones that have existed since the 1990s, when we went from analog to digital in the early 1990s, and by the way, Raleigh, North Carolina was really a hotbed of the leadership the technology that led the analog mobile phone service to digital in the early 1990s. Ericsson had a very large operation here in Research Triangle Park where they pioneered TDMA and the second generation digital cell phone standard for the US, GSM in Europe. And CDMA evolved to 3G, and the world went to OFDM 4G technologies, which is now being rolled out around the world. And you can see with each generation of technology in the cellular mobile commercial industry, we're seeing orders of magnitude increases in data rates from kilobits per second on 3G to tens of megabits per second for 4G, with a goal in the next few years to take 4G LTE, long-term evolution with OFDM and MIMO, to try to get that up to 500 megabits per second, maybe even a gigabits per second. But you're going to see around 2017, 2018, 5G, and you're going to see data rates from 6 to 50 gigabits per second over the next 5 years to your mobile device. Now, to put this in context, that means downloading full-length feature movies in a matter of seconds to your portable device. That's coming in 5 years. The question, though, is how do you do it? There's only so much spectrum used today in the cellular world. And when you look at what's happened in the wireless industry over the last 40 years since the first generation of cellular, you can see Moore's Law has given us great benefits in computer clock speed. If you look from left to right, from 1976 to 2016, over 40 years, we've seen a 5,000 times increase in your clock speed on your portable computer. You've seen the personal computer memory size go up by 2 million times, 6 orders of magnitude. Yet in the history of cellular, the frequencies that we use for our cell phone has barely budged, from 850 megahertz to 2.5 gigahertz. That is, Moore's Law has given thousands or millions of times benefit, but the carrier frequency used by cellular hasn't even gone up by an order of magnitude. And that's all going to change. Because when you go up at higher frequencies, you get for free a percentage bandwidth that gives you much greater spectrum. Think about a 1% bandwidth at 1 gigahertz, and that's 10 megahertz. You go to 100 gigahertz, and a 1% bandwidth is 1 gigahertz carrier bandwidth. So you're going to get huge channels if we can go up to the millimeter wave frequency regime. So it's wide open, lots of spectrum. This chart shows, going left to right, an order of magnitude in carrier frequency, starting the very top. That's where submarines talk, from through 30 kilohertz to 300 kilohertz. In the second row, AM radio. How many here have listened to AM radio? Raise your hand if you've listened to AM radio. Wow, about half. That's pretty good. So raise your hand proudly if you've never listened to AM radio. Raise your hand proudly. Oh, come on. Half of you. Half raised their hand, so half of you should say no. Let me ask again. How many of you have listened to AM radio? Raise your hand proudly. Okay. How many have not listened to AM radio? Raise your hand proudly. Okay, good for you. See, only one has not. When I asked this question when I was at UT Austin 5 years ago, no one had listened to AM radio, but maybe they were like you and just didn't admit it. But the fact is, you don't get your radio, your music off the air anymore. You don't get your news off the air. You get it off the web. You get it off your smartphone or your computer, probably. How many people listen to their music on an actual radio today? Raise your hand. In the car. Okay, and how many don't listen on a radio when you're not in the car? How do you get your music? Raise your hand if it's not by radio. Look at that. That's totally changed in the last 10 years, and that was made possible by 4G LTE. And so now you have AM radio stations around the country with these giant towers selling their real estate so that land developers can build houses because no one listens to AM radio anymore. But this spectrum chart shows you the AM radio band from 300 kilohertz to 3 megahertz, and then you have shortwave. You have cellular is here from 300 megahertz to 3 gigahertz. Each row is a decade of frequency. Yet the entire world spectrum, AM, FM, satellite, TV, cellular, FM, all of that fits in this tiny area at the 60 gigahertz band. So all the spectrum we've ever used in the history of the world is available in the IEEE 802.11ad standard. And that's the tip of the iceberg, because people like Brian Floyd and folks working in industry are developing integrated circuits that are going to work well up above 60 gigahertz, hundreds of gigahertz. So that chart shows you how much spectrum is available when you move off the first 6 rows and go to the 6th and 7th row in the millimeter wave frequencies. So it's really a wild new spectrum frontier where there's more bandwidth than ever has existed in the history of the world. And when you go up to these higher frequencies, the millimeter wave frequencies, which we call 30 to 300 gigahertz, industry calls it 10 gigahertz and above. So, today's cell phones are at 2 and 3 gigahertz. And at the wavelength at 2 and 3 gigahertz is about the size of your phone. Quarter wavelength of your cell phone, quarter wavelength of 2 gigahertz, about this big. You go up to millimeter wave frequencies where instead of at a couple of gigahertz, you're up at 30 gigahertz, the wavelength becomes about the size of your fingernail. And if you put it on a high dielectric constant, the wavelength becomes the size of a human freckle, which means you can start to put lots and lots of antenna elements on the same physical size of that phone you have that right now only has a couple of antenna elements. So this is a picture of a chip we made about 7-8 years ago. And there are 16 antennas on it. It's a phased array, and you can actually put 16 elements on your thumb. And so handset makers like Samsung and chip makers like Qualcomm are busy figuring out, and researchers at NC State and other places are figuring out how to make very power efficient antennas that could fit in handsets that can have hundreds of antenna elements that will basically turn your phone from what it is today, where it radiates a lot of energy everywhere and hopes it gets to the base station, to these very large arrays of very narrow beams that can focus energy and can overcome the free space path loss that occurs as you go up with the square of the frequency. You get is 20 dB loss per decade of frequency. So you'll take a loss in the free space, but you're going to get it back in the antenna gain. So all of our phones in the next few years, as we move to millimeter wave, will go from these antennas which spray energy everywhere to basically creating these very narrow beams that will follow us as we go and will bounce off the proper places as we communicate. And it wasn't so long ago that people did not think millimeter waves were possible. In fact, even today, a lot of the die-hard engineers in industry don't believe millimeter waves will work. But all of that in the last year has really started to change as more and more engineers around the world have done their own tests and have seen that indeed millimeter waves will work. In fact, they could work even better than today's cellular because of this dimensionality of space, this spatial processing that we can bring to the mobile and to the base station that's never existed before. There are 3 main focus areas that the naysayers over the last several years have put forth, and I've been on the forefront of proving to the world that millimeter waves not only will work, but it's the only solution to bring Moore's law to you and I, to the cellular device. It's the only way. First, they say, well, millimeter waves are too lossy. You just can't propagate at these high frequencies because of Free's law. Free's free space law says that as you go up in frequency, that is, the wavelength gets smaller, you get a lambda squared. You get a loss that's a square of the frequency. And Yep, that's a big loss. But when they do that mathematical comparison, they forget that Free's law is assuming you have unity gain antennas at every different frequency. The fact is, if you have unity gain antennas, the antennas shrink at millimeter wave. If you keep the millimeter wave antenna the same physical size, you actually get a gain of the antenna, a directionality that's exactly equal to the loss. So it's actually a wash. There's no fundamental difference to millimeter waves to any other frequency in free space. Now it's true, obstacles will look more opaque, weather effects will hurt millimeter waves more, but if you're in free space, there's absolutely no difference, as long as the physical size and the antennas are kept the same, between low frequency and high frequency, which many engineers are finally starting to get. So you can overcome this free space loss with antenna gain. You just now have to steer the antenna. Great research challenge. Secondly, shadowing. People say you won't be able to penetrate buildings. You won't be able to, your body will block the signal. It's true. But the beautiful thing about the world of millimeter wave is everything's reflective. We have a reflection coefficient of 0.6. Energy that bounces off us gets received somewhere else. And in fact, the blockage between building partitions will actually be a win for wireless, because you'll be able to keep the interference outside the building from penetrating inside the building. We just have to deal with the handoff. And in fact, this scattering phenomenon allows wireless to work in non-line of sight, which no one believed till we proved it to the world in Manhattan in 2012, when we went around NYU's campus and could make 200-meter non-line of sight connections with very low power in the heart of New York City. The world didn't believe it. And then all the big companies started making the measurements using the same system I'll show you. And they started to see it worked in Beijing, it worked in Seoul, it worked in Los Angeles. And now the world believes millimeter wave will happen. In fact, it's this reflection and scattering that's a total game changer at millimeter waves that we didn't have and don't have in today's cellular. Today, we rely on diffraction for your 4G phone call to work as you walk out this room and down the hall. You rely on the energy to be able to bend. You don't have the advantage of a steerable antenna, but you do have the advantage of diffraction, which keeps energy alive. At millimeter waves, going around a corner creates 20, 30 dB of loss. So we're going to have to rely on the adaptive antenna, the steerable antenna, to create beams that adapt to where we are and make sure the energy is always in play. If we do that, we have no loss of signal. But we don't have the benefit of diffraction. As you go higher in frequency, you lose diffraction, but you gain scattering, because everything starts looking rough. So you get a lot of rough surface scattering and a lot of energy is kept in play. So we showed the world that it worked. And this is just the tip of the iceberg, because when you finally realize that there's really nothing different about millimeter wave and free space, that is really about the antenna and building signal processing methods and devices that can track the energy, you start to see that there's a whole new world of spectrum that we never contemplated. This chart shows the attenuation in air as you go up in frequency. Another commonly held myth by the industry has been, until recently, that at low frequencies, like 1 to 20 gigahertz here, you have very little attenuation due to oxygen, due to atmosphere. Virtually nothing. 1/100th of a dB. Well, the 60 gigahertz band, where unlicensed Wi-Fi exists today for 802.11ad, it was allocated by Ofcom and the FCC 20 years ago because they knew there was an oxygen absorption region at 60 gigahertz. 20 dB per kilometer loss. It's a factor of 100 signal loss above free space loss. But if you move to 70 gigahertz, that drops well below 1 dB, down to 1/10 of a dB. You see, when you go up to 300 and really up to about 400 gigahertz, there's very little atmospheric loss. It's a dB per kilometer. Really very minimal. And there are these different zones, different frequency bands, which will be very well suited for mobility, like at the 80 and the 230 gigahertz band. And then there are these natural high attenuation where oxygen molecules have resonances which cause loss, particularly at the 180, 320, and the 380 gigahertz band. I really love the 380 gigahertz band. Here's why. We came up with this idea of a whisper radio, where you could have a wireless device that's maybe 10 gigahertz bandwidth wide, super wide bandwidth. Yet it's very attenuative, so that a few feet or even a foot away from a person, the signal decays so rapidly. Basically, it's guaranteed security. You operate at these frequencies, the signal doesn't go anywhere, so it's like you could have a private conversation and no one hears you. Can't be eavesdropped because there's such rapid attenuation. But you have so much bandwidth, you are guaranteed for, say, a low data rate communication. You have so much frequency diversity that you could actually improve the connectivity quality better than a copper wire. Because you have so much bandwidth. So you actually can replace copper wires in automobiles, tanks, vehicles with very wideband, very secret wireless communication. We will see these products, I predict, in 10 years. It's just a whole new world. And 10 gigahertz of bandwidth today is just unfathomable. But it's going to be a tiny part of the spectrum if we go up to millimeter wave. So this basically is a whole new dimension, and it shows that these things will happen. In fact, the FCC realized this, and we worked with them, as I'll show in a moment, to show that even with rain, you still, you have 25 millimeters per hour, it's an inch per rain. You have heavy attenuation, 10 dB per kilometer. That's a factor of 10 loss of signal over a kilometer at 73 gigahertz. But for small cells, 200 meters, that's only 2 dB. And you make your antenna a little bit larger, kick in a little bit more gain, you can overcome the rain. And the FCC followed our work and led the world last year in opening up an unprecedented spectrum ruling called Spectrum Frontiers. They allocated 28 gigahertz of spectrum. 28 gigahertz. The whole mobile industry in the U.S. has shared maybe a fraction of a gigahertz of spectrum. And in one rulemaking last year, they've opened up 28 gigahertz of spectrum, FCC 16-89, new frequency bands at 28, 38, 40, and they've made a new 7 gigahertz unlicensed band at 65 to 70 gigahertz, and they opened up to 81 gigahertz. So the U.S. is the first market in the world that's made millimeter wave spectrum available. And you've probably read about Verizon and AT&T doing trials. They'll probably start in millimeter wave backhaul first for rural. And the beauty is you now can just kick in a little bit more antenna gain or a little bit more RF amplification to overcome the rain. And if you can make steerable antennas and can design the system for worse rain events, kind of like DirecTV or EchoStar has to do, you actually can provide real mobile coverage. So I wanted to show you kind of where it started and some of the work we did and some of the challenges we've had to overcome and that the industry is now working to overcome. I like to say it all started at NYU Wireless because we had shown at UT Austin that you could get coverage on the UT campus with millimeter wave base stations and horn antennas. And Samsung, I had been pitching this idea actually for many years. I've always believed in millimeter wave. I always knew that the spectrum would have to come to millimeter wave. I did work in MIMO. I knew MIMO could bring you capacity, but until you got the RF channel bandwidth wide enough, you would never be able to see Moore's law come to wireless. I mean, look at Shannon's capacity theorem. C equals B times log 2 1 plus SNR. B, the bandwidth, is in front of the logarithm. B is your biggest multiplier. You've got to get B, the bandwidth up. How do you get the bandwidth up? You have to go to millimeter wave to get the wider channel bandwidth. So that was the only place it could come from. And so one of the exciting things, it was very hard to leave UT Austin. Have a lot of friends there and loved it there. And started a great wireless center with a lot of great colleagues. But I knew if I could make it in New York, I could make it anywhere. And so when NYU recruited me, and they recruited me, boy, they came after me out of the blue. I negotiated a lot of things, but one of the things I negotiated was the ability to access any NYU property. I got the president to agree that I could have the students do research and we could access any NYU building we wanted to in Manhattan. I had to have that commitment. As I told them, we are going to invent the future of wireless. And if you can prove it in Manhattan, the world will believe it. And so they believed it, and they gave us access. They don't like students going on roofs. And so we went out on the roof, and we set up equipment, and we built, at that time, the world's fastest channel sounder, which basically hits the channel with an impulse, bing, and you see where the delays go, and you measure the power. And we use spread spectrum because you can get some efficiencies. And we went to the top of the business school, Kaufman, on the bottom right, and we went onto the gymnasium. We put these base stations up, and the students worked very hard during the summer of 2012 at 28 gigahertz. And we collected measurements as if we were a mobile device with an antenna that could scan in azimuth and elevation. We had to use mechanical horns because these phased arrays didn't exist yet. In fact, they're still hard to get. There was a company, Cybeam, that made one. We have one in the lab. They got bought by Lattice Semiconductor, and they threw the whole business away, which is a shame. And we're working on phased arrays, but they didn't have them in 2012. So we built this channel sounder, and you can see the Brooklyn Bridge in the background on the left. And we went out and measured, and we were amazed. I had a hunch it would work from our work at Austin, but I didn't realize it would work so well. I didn't realize with less than 1 watt of power, and with 25 dB gain horns, which have an aperture about this size. You could put that on a phone. And with a base station with an aperture this size, much smaller than what you'd use in a commercial application, and with less than 1 watt, we were 80% of the time down non-line of sight streets able to receive a strong signal. 10 dB SNR or better. That is, we could make a link at random locations throughout Manhattan with these steerable antennas. We were shocked. We were overjoyed. And the world was amazed. We had a lot of doubters. We even went to 73 gigahertz the next year. Nokia came to us and said, wow, can you go up to a higher frequency? And so we did 73 gigahertz and did the world's first trial at 73 after we proved 28 would work. By the way, the FCC chose these bands. These are FCC bands now. And we went out and did the same measurements at the same places and found, remarkably, there was a little bit more outage, but not that much more. 65% of the time we could make the link. And we found out that the channel is very, very directive. That is, we came up with this idea of lobes, energy that travels in these small spatial lobes created by the physics of the urban environment. Energy doesn't go everywhere. These are directional antennas scanned over 360 degrees, and the energy arrives in very distinct lobes. And the multipath is very comparable to today's cellular. That is, the channel is not that different except for the directionality of millimeter waves. That was very interesting because it meant that you could use these smart antennas. These smart devices, these antennas that can form beams, would actually allow you to create links. And we made a channel model. We announced it at the FCC the day the FCC had a public hearing. And now there are over 6,000 engineers around the world using NYU SIM. Anyone here using NYU SIM? Anyone here? No? Okay. It's an impulse response channel modeling tool. It's free. And companies around the world are now building the air interface so they don't have to go out and make the measurements that we did. It's very hard work. So it will reproduce random impulse responses in time and space. So if you're looking at various channel coding approaches or studying MIMO or trying to figure out bit error rates or capacity, you can use this. And in fact, a number of major companies are comparing this to the 3GPP channel model. We have some of these elements that have just put into the 3GPP as the global cellular standard that's working on the air interface. Those companies are using this simulator. So that's publicly available. It's a tool you can use in your research. We're using it to study massive MIMO and comparing spectral efficiency of different air interfaces. But here's what's amazing, and this is probably a good lesson for the students. Industry has very different motives and reward systems than academia. And most of you will go into industry. And what we found as we started working with these companies that were sponsoring us, we had a lot of companies who were funding our work. We started to realize that the channel modeling standards and the basic science used in the standardization process often gets politicized. You see, 3GPP, which has been the governing body for all the cell phones made for the last 4 generations, all have focused on 6 gigahertz and below. That's the world everyone knows. It's all the data they've used and all the cell phones work there. But here were these new measurements, here were these new results, and here were these new frequency bands that are at much higher frequencies. And so what's been fascinating is to watch the industry try to grapple with how to take all their old code, all their old models, and try to incorporate the physics and the reality of above 6 gigahertz. So there's been intense work by all these companies over the last 2 years. And what I wanted to show you is that in 3GPP and the ITU, the International Telecommunications Union, which generally is a standards organization that provides the spectrum allocations around the world. They have these WARCs, these World Radio Conferences. There'll be WARC 19. 2019 is when all the 5G spectrum will be allocated throughout the world for millimeter wave. And so countries are getting ahead of the game. The FCC got ahead of the game. They've made the allocation years before the world will. But and they're hoping to get the world to come to our market, to the U.S. market. But in 2019, the allocations will be made, and 3GPP as an industry will provide their information and desires to ITU, and lobbyists will go from the different governments. That's all in the process now, but what we found is that the channel models, which is kind of the ground truth from which you can build algorithms, compare devices, compare approaches. The channel models have problems. They're not based on physics. My students and I found this when we started looking at the measured data. We found there was a very simple channel model that's very easy to describe all the propagation from 1 to 100 gigahertz and above based on the famous Harold-Frees free space equation in the first meter. But the models that exist in 3GPP made no sense. They look like random numbers. They're just people putting a bunch of data together and engineers coming up with fancy curve fits that have no basis in physics. I was surprised at this. So my students and I, we decided to talk with some of the companies and learn the rationale. And they said, well, there's a few people who thought it was a good idea and we didn't pay much attention. So we thought we'd contribute what we had learned. And NYU proposed this very simple model to predict the signal level at some distance away. It doesn't matter if it's narrowband or wideband. The industry was using what they call the alpha, beta, gamma model, which has 3 parameters, alpha, beta, and gamma. And the alpha, beta, and gamma are curve fits to a bunch of data over different frequencies. Well, we discovered that everything is fundamentally based on free space in the first meter of distance. Because if you're at an antenna, no one's in the way of the first meter of a base station. So if you put a physics-based received power at 1 meter, and that's a function of frequency because of the f squared in that formula, it turns out it always works. The slope is always the same at any frequency. So you only need 1 parameter. You only need n, a path loss exponent. So industry was using 3 parameters. We proposed 1 parameter because my argument as a professor was that we're going to have young engineers coming into industry. They're going to look at this standard, and they're going to want to know why the model is as it is. And right now, there's no good answer. It looks like random numbers. And we compared the goodness of fit on the far right, the standard deviation, to measure data from 5 companies, 30 data sets from 1 to 73 gigahertz. Nokia, Qualcomm, Samsung, Ericsson, Huawei. And over all those data sets, the 3-parameter ABG model and the close-in free space reference distance model had virtually identical standard deviation. We use 1 parameter. Industry's using 3 parameters. If you're going to use 3 parameters in a model, you should get a big improvement, right? Otherwise, why have it? And in fact, the ABG model sometimes gives non-physical based parameters. This is the alpha, the path loss with distance. 1.1, that's like a waveguide. So there were parameters in the ABG model that made absolutely no sense. So we published this, and we also showed the value of having a 1 meter reference distance to the industry. And some companies have agreed with it, some haven't. But look at the distance in free space. If you use a simple 1 meter free space reference distance, you can now compare any frequency, any antenna gain very easily. Because there's just 1 parameter you have to keep track of. And if you make that parameter the same, you can plot a curve like this. And look at the distance you can get for n equal 2 free space. You can go 10 kilometers with very meager antenna gains. 30 dB combined antenna, theoretically, you could go 30, 40 kilometers if you don't have curvature of the Earth. This blew people away. It shows that you could actually have, in clear weather, rural millimeter wave links with very small antennas. You know, 20 dB antennas like this at 28 gigahertz. And you could go huge distances, but if the n, that single path loss exponent, is, say, 4, the distance goes down to 200 meters. So we showed the industry this, and then we showed the errors that happen with the ABG model. The ABG model actually predicts more signal strength in non-line of sight than physics gives you in line of sight. Makes no sense. It makes no sense. The industry's been using a model in 3GPP that predicts non-line of sight is stronger than line of sight within 50 or 100 meters. So I brought this up to the 3GPP. I submitted a friend of the standards body because no academic has time to deal with standards. And what happened is they didn't want to look at it. Some of the companies said, we'll just put in a patch. We'll put in a patch that says, if signal in non-line of sight is stronger than line of sight, default to line of sight, even if you're in a non-line of sight environment. Anyway, it was very, very amusing. So what I learned very quickly is that industry often wants to stay married to exactly the same models. And the people told me, even with these errors, I showed them there was 6 dB overestimation of loss. That is, the industry has models that deliberately predict more loss. Why would you do that? To predict less interference. To be able to sell the carriers more equipment. And then, oops, there's more interference. We'll now sell you more equipment after you've installed it. So, that's the motivation of industry. It's not the pure science. But this one, I had to wail on them. Let me go back to that. This is funny. This is the published 3GPP model for rural macrocell. 4 lines of equations. This is for rural. Notice there's parameters there for the width of a street, height of a building. I mean, why do you care about height of a building in rural? So one of my grad students, George McCartney, studied the history of this model, which is in the ITU and 3GPP standard today for above 6 gigahertz, ratified in September. The history of this model comes from downtown Tokyo in the 1980s. This is supposed to be a rural macrocell model. Fact is, no one's ever measured it. Ericsson made a few measurements only out to about 100 meters, and this model goes to 10 kilometers. So the industry is working off a rural macrocell model that's never been tested, never been proven. In fact, I asked my board, I said, why is this? And they said, well, we don't believe rural will ever be used for millimeter wave. Of course, what do you see in the papers today with Verizon and AT&T? Where are their trials? Their trials for millimeter wave are fixed and suburban, and they're going to rural. So we realized this was an opportunity for academia to help fill a hole, because there's nothing intuitive about these models. I mean, I don't know if you take a course on wireless here and you talk about propagation, but I'm sure Professor Stansel looks at that formula and probably says it's not real intuitive. And it's not. So we decided to look at what that model does if you simulate it. And we found out that you could replace that very, very complicated 4 lines expression with the simple 1-parameter close-in model. If, for example, the red and the blue curve are a comparison of the close-in versus the RMA current model. Very, very close. And so we set out to do the world's first careful rural macrocell measurements at my home in Reiner, Virginia. And we decided to do this in a very rural area, but to use a very tall base station. We actually used my house, which is on top of a ridge. And we wanted to see if we could go 10 kilometers, first of all, because no one had ever reported in the scientific literature millimeter wave at 10 kilometers, yet there was this channel model for it. So that was the first question. Can you go 10 kilometers? The second question is, how well will that very complicated published standard work in the real world? And so we went to my house. Here are some of the students setting up the base station transmitter, looking out over the vista. This is a view from the front porch. And in fact, you could see Virginia Tech a little bit to the right of center, about 20 miles away. When they play a football game, you can see the lights of the stadium. This is where I go to think, and it's very peaceful up there. It's also very out of the way. If it snows, I can't get up there. So and then the students drove a van for 2 days all around out in the front, out to 10 kilometers to see if they could measure signals. This is a schematic that shows what it looks like. We're at about 110 meters above the terrain, looking out, and these are the locations of where we measured. We measured red is non-line of sight, blue is line of sight, and these are the first rural measurements in the world. And we were amazed that we could go out beyond 10 kilometers in some cases. We had an outage probability of about 20% of all the locations we tried, much better than we thought it would be. And we take this equipment and we take these antennas and these horns and we'd go out and pull across the side. There's a line of sight with just a tree blocking going back to the house. There's an example of looking back to the house with a tree blocking. We call that line of sight. This is 5.7 kilometers away, a non-line of sight with a small hill. There's the house up on the mountain and a line of sight location 7 kilometers away. And when you plot all the data, what you see is this very simple 1-parameter close-in path loss model predicts with very good accuracy. When I see very good accuracy, with a standard deviation of less than 7 dB and less than 2 dB for line of sight, Free's free space equation really works well. Very simple. And so we were able to predict, this is the enlarged view, this is line of sight behaving very well, as long as there's no rain or fog, and then non-line of sight. These are very comparable to today's cellular path loss exponents. In other words, the channel is not that different. And so we verified this channel model and proposed it for a rural macrocell for 5G. So they're considering it, 3GPP is considering it, but this is a very simple equation. There's one equation for line of sight, one equation for non-line of sight. There's just one parameter. There's one parameter, and that is this. It's N, 2.16 or 2.75 for non-line of sight. So now we understand the rural environment. We understand the urban macro, urban micro. Engineers now have the tools needed to start doing capacity analysis, system design, start provisioning, distances, powers, and the rural is known. Now, it's not just enough to understand the channel, and there's a lot of, hopefully you see the challenges. Challenges are creating antennas that are not mechanical horn antennas, but are actually on a circuit board or embedded on the skin of a phone. Low cost, high reliability, power efficient, creating beams not with a horn, but with a phased array. And the challenge is now, once you understand the link, is figuring out the air interface, figuring out how much overhead will be used, what will the latency be, what will be the packaging of the bits. 500 nanoseconds, will it be 5 milliseconds, what will the frame rate be? And we have some of these things in a book that Robert Heath and I wrote called Millimeter Wave Wireless Communications, where we put forth some of the ideas that are now starting to be used in their deliberations in the industry. But before we ever get to 5G, there needed to be a final coup de grace, if you will, convincing of the world that capacity would really be there. It was one thing to measure the streets of Manhattan and show that non-line of sight would work. It was another thing altogether to prove that in a true real-world millimeter wave mobile environment with people using their phones, that you'd have enough capacity to justify the investment. And that's work that Sandeep Rangan and I did with Elza Urquhart. Right after we made the measurements in 2012, we put together a real cellular system simulator, the kinds that are used at companies like Qualcomm and Samsung. And we ran a bunch of simulation assumptions that are used in industry, and we showed that with very moderate antennas at the base station and at the mobile, that is using 8x8, 64 elements at a user equipment. 64 elements is very viable at 73 gigahertz. Or just by using 4x4 at 28 gigahertz. By the way, that's about exactly the same gain, because it's the same physical area. So it's the same gain at both frequencies. We showed that the capacity, indeed, unlike today's cellular systems where you have this kind of waterfall, capacity goes up linearly. And we were able to show that with this linear capacity increase, you get huge SNR on many links. And when you have huge SNR, when that signal-to ratio is high, you can then use M-ary keying, 256 QAM, 1024. You can get the huge data rates needed. That's how Wi-Fi works. When you have a good channel, we use a much more complicated modulation constellation. So here we showed that your data rates could be at the cell edge over a gigabit per second, 1.468 gigabits per second on the uplink, 1.54 gigabits per second on the downlink. True multi-gigabit per second data rates throughput to mobile devices. And we published this in 2014. And basically, this required 1 gigahertz channels. Today we use 20 megahertz. So if you increase the channel by 50 times to 1 gigahertz RF bandwidth, which will be easy at millimeter wave, you're able to really ramp the throughputs up to over a gigabits per second. And at the cell edge with only 5%, the worst 5%, your average throughput was still on the order of 28 megabits per second, where today's LTE is 1.8 megabits per second. So right now you have terrible coverage on your 4G phone if you're on the edge of the cell. You get maybe a megabit per second. You think it's broken, right? Because you're getting 5 or 10 megabits per second when you're good, and then you're down to 1 megabit per second. The cell edge is where the carriers really care about it, and here we're 25 megabits per second. Now this was very conservative, but it showed the world that it was worth the investment. And then Nokia came along, and they put in a few extra twists that would be done in a real commercial system, and showed 15 gigabits per second peak rate in simulations. That was they were actually doing that at the same time, and we collaborated. So these works showed 15 gigabits per second to your phone. I mean, think about that. 15 gigabits per second is more than you're getting to any computer connection you've ever used in your life. And that's coming to your phone. It's going to be a wild world with so much content coming to your device. It's real. It's going to happen. There'll be ways to reduce the outage, denser cells, small cells, smart repeaters, relays. But the bottom line is, I call this the renaissance of wireless. We're going to bring all the content you'd ever want and applications we've never thought of with such bandwidth. You know, the challenge is the backhaul, getting the bandwidth to the base stations, and the companies are working on that now. Fiber's the way to go there, and there'll even be millimeter wave backhaul. But we're looking at a future where it's going to be wild, it's going to be wonderful. It's wide open, apps that we've never thought of, virtual reality, gaming, multi-sharing, you know, physical presence in 3D, graphics, smart cars. This is all coming to a cell phone near you in the next 5 years. Thank you very much. I think we have a little bit of time for questions. Yeah.
So you debunked a lot of these engineering myths about going up to millimeter wave. You make it sound very easy now. So what, on the physical layer, you're talking about antennas this big, what are still some of the outstanding challenges on implementing these kinds of systems?
Yeah, and I met with a lot of faculty who have a good idea of what those major challenges are to reach this millimeter wave future. Some of the biggest challenges are in power efficiency. RF power amplifiers that are efficient of using the battery that can get us the efficiencies and power levels we need. Right now we're at about 15% power efficiency up at millimeter waves. To give you an idea, you're able to get 40-50% power efficiency on RF amps, even higher in today's 4G phones. So that's a real device semiconductor issue, whether it's CMOS or SiGe, probably SiGe on the RF amp, maybe even some 3.5 materials, GaN. But that's one big issue, how to get power efficient amplifiers up at these kinds of frequencies. The other big issue is how do you combine the amplifiers that will be used in a phased array antenna. You think about it, interconnects are very expensive from a power standpoint. Think about running a coax at 50 gigahertz, and there's a lot of loss just running a little copper wire. So integrating the electronics and allowing the power to be distributed to the multiple antennas and combining those in a very power efficient way is a huge bottleneck, and companies are working on it very hard. Brian Floyd told me about an interesting idea. I heard it about it in passing, but I really didn't think it was realistic. The idea of putting a mixer first before a low noise amplifier. Very interesting idea. What you do is you bring all the processing down to baseband if you can make a super wide band low noise. It's a key low noise mixer. Fascinating idea. In fact, that's what changed the world when we went from analog to digital. I'll kind of show my age here. One of the most brilliant things I've seen in the history of the wireless industry, and I've been in it for a long time, really from the beginning, Qualcomm changed the world when it proposed CDMA in the early 1990s. I was lucky. I was right there when it happened, and I had a front row seat, and I got to participate. What Qualcomm did is they realized that Moore's Law was scaling so much faster on the baseband processor than it was in the RF filter domain. And everything up until the early 1990s in mobile radio used a narrowband radio channel. It was FM, and you had to put a filter on it. You had to build a filter, a high-Q filter. It was expensive, it was bulky. And Qualcomm realized if you widened the bandwidth and didn't care too much about the filtering, and you went to CDMA, Code Division Multiple Access, you'd then bring the processing power and all the filtering down to baseband, where you could take advantage of Moore's Law and signal processing. So that's going to happen again, I think, in millimeter wave. You're going to bring all the processing down to baseband that's going to try to make up for the difficulties up at the RF. But right now, the RF is the struggle for power efficiency and combining power. Those are two big bottleneck issues I see. The third one, in a practical carrier standpoint, is the backbone. Believe it or not, today in most 4G LTE cellular systems, it's not the air interface of the LTE base station that's serving your phone. It's actually the baseband that Verizon or AT&T or T-Mobile or Sprint is able to get from the Time Warner or AT&T who's providing it, often limited to 100 megabits or a gigabit per second. You can't get more than a gigabit per second to a base station. You're at millimeter wave, and if we're all drinking a gigabits per second or 10, you need 50 or 100 coming to that base station. So that backhaul is a big challenge, how to get that bandwidth. Fiber is going to be the answer. So you're going to see the companies and the countries like Korea that have the installed fiber rolling this stuff out before the rest of the world. Other professors or students might have other ideas what the key challenges are. Yep.
The trend today seems to be people ditching their landlines and using their mobiles as their primary phone.
Yeah.
How well is millimeter wave going to work when I'm surrounded by four walls in my bedroom?
Yeah, well, that's a great question. In fact, I've done that. I've ditched my landline. We just moved to Raleigh. I just bought a house in Raleigh, so I'm your neighbor. I'm very excited to be here. And this is the first house I've ever owned where I'm not putting in a telephone line. I actually have, I got the AT&T leaders to run a 1 gigabit per second fiber optic cable to my house. And I'm going to have Wi-Fi and UVerse and no landline. My wife was like, I don't want that phone ringing. I'm like, okay. I'm doing it. I'm cutting the cord. That's the future. In fact, I didn't realize it, that most people now, these new houses that are being built today, don't have landline put in. They assume you're not going to use landline. Kind of blew me away. You're going to rely on wireless access points in the home or in the office for indoor coverage. You're going to rely on Wi-Fi, and you'll have Wi-Fi to 5G handover. They're already working on it now. That's what unlicensed LTE is kind of about. You're going to see that grow very quickly, and so you won't be without service. You'll just go from your own Wi-Fi network to your 5G outdoor cellular network seamlessly. That's the future. In fact, we kind of do that now, don't we? Don't we now, if we're at a good Wi-Fi spot, we're kind of on the Wi-Fi? Yeah, we can even Skype and even make phone calls. The Apple phone allows you to do cellular over Wi-Fi. So that's how we'll solve that indoor-outdoor issue. Yes?
Was it a good idea for FCC to preempt ITU in allocating these frequencies? Because if ITU goes the way FCC, then we're the spearheads. But if they go any other way, then we're the weird ones.
Great question. Was it wise for the FCC and Commissioner Tom Wheeler to go in front of the ITU World Radio Conference in naming the spectrum allocations? I think it was a brilliant move. I see no downside. Here's why. First of all, it turns out that the FCC's spectrum allocation is very close to what WRC 15 put up as a straw man. That is, except for the 28 gigahertz band, all of the FCC spectrum aligns with an ITU first order allocation. So they got that right. Second thing is, what it does is it builds a marketplace. It allows the U.S. to be the first country in the world where commercial service, commercial products, vendors can install their equipment. And the U.S. market's big enough that if they get enough uptake, they will get the chip companies like Qualcomm and Broadcom and MediaTek and Intel to invest in serious production runs. And once they commit to the serious production runs that get these devices and the handsets to consumer prices, it's then very easy to justify a simple change in frequency for another government, for another country. Fact is, you don't want to do that. The reason why Wi-Fi is so popular around the world is that there was harmonization of the spectrum for Wi-Fi in Japan, Korea, Europe, South America, US, North America. And so one chip maker could make a radio that had all the bands in it, and you turn them on and off at the different frequencies for the different country. That's what your laptop does, or your cell phone does in Japan versus here. So the key is to get the sockets, to get the chips made first, and to build a market. And so the FCC is trying to get out in front and get the best equipment to the U.S. first. And I think it's a great move with no downside. The downside is to wait, and we didn't wait. It's kind of fun because as an academic, it's fun to see your work turn into the next generation of cellular. Yes.
One more quick question. So, at the end of the day, my understanding is that the amount of energy per bit that you can save using all of these techniques, maybe you can get a factor of 5 or 10, but not a factor of 1. And you're talking about data rates that are perhaps 3 orders of magnitude higher, and on the other hand, we're talking about savings of energy per bit of maybe optimistically order of magnitude. So doesn't that mean that the battery will need to be used? Something's got to give here, right?
I take issue with the savings of energy per bit. Actually, we published a paper 4 or 5 years ago, and it's just starting to catch on. It's a consumption factor theory. It's a theoretical analysis for how anyone could take any chip, any system, any network, any architecture that has a source and a sink and actually compare the power efficiency, consumption factor. And it turns out you really reduce the energy per bit as you go wider bandwidth. You really get like a scaling. So we drop the energy per bit by several orders of magnitude as the bandwidth goes up at millimeter wave with the directional antennas. So I take a look at that consumption factor theory paper. The energy per bit really does go down as you get wider bandwidth. And in fact, that's the interesting thing. The theory shows that if you can make your portable device consume most of its power not in the source to sync radio transmission, but in the CPU or the screen or applications, that's where you get the biggest savings. In fact, most of the energy is going more and more towards not the radio transmission, but towards the device, the lighting, the apps, off the radio channel. So the energy per bit in the radio channel actually is, we're really driving that down as we go wider bandwidth. It's not intuitive, but it's remarkable. And these directional antennas give you the gain that actually can do it. You actually can overcome free space loss by directional antennas at both the transmitter and receiver. It's the first time you can actually overcome the loss with directionality on both ends of the link.
Thank you. We'll need to wrap up. Let's thank Professor Rappaport one more time.